Okay, I guess it's time to get started. Okay, are there any questions before we get started? No questions, then maybe you can get started then. Today I'd like to talk about the solution of a point source on top of the, I guess maybe I should start with this slide. Okay, the spectral expansion of a source field, which is a point source on top of a layered medium. So we will have to first deal with the spectral expansion of a point source. So it looks like that my camera is not working. My other camera is not working. So I have to use the camera of the laptop, and hence you're not going to see my face very easily. So there are lots of knowledge at this point. I suppose I feel that this is like swimming in an ocean of knowledge. It's going to be lots of knowledge to learn, but I hope you will find it fun that you're learning so many things at this point. Okay, so we'll first talk about the spectral expansion of a source field, putting a point source on top of a layered medium, and then look at the dipole field and so on. This is usually called the Summerfield problem. Summerfield was the person who actually first solved this problem many, many years ago. Maybe perhaps around 1909, he solved this problem. Summerfield is a remarkable person because he actually has maybe 4 Nobel laureates for his PhD students. This is some of the, let me see. He has a number of awards. He did a lot of great things. Many of his students went to win Nobel Prizes. Okay, so he's a very impressive person, but let's see what this Summerfield integral is. So first we study this problem of the spectral representation of sources. Okay, and how do we solve this problem when we have this thing to solve? Let me see. Okay, so the first thing we need to do is actually the problem that we want to solve is actually this problem. If you have a point source, and if you put this point source on top of a layered medium or a half space, okay, the half space can be very simple. It can be vacuum up there. It can be some other media down here. And some of us was interested in this problem because it was very important for radio, okay, radio propagation. For instance, if you have a AM radio station, and if you have a tower, and you like to see how radio wave propagates on the Earth surface, okay? So in order to solve this problem, you first have to tackle the problem of expanding the wave coming from a point source. Okay, this usually we know is a spherical wave. We like to convert this spherical wave into summations of plane waves and evanescent wave. Okay, how do we do that? To do this, we have to use the Fourier transform technique. Okay, and so let's just do the first part, which is actually to solve this equation using Fourier transform. Say if I have this equation, x, y, z is equal to delta r, which is essentially delta x, delta y, delta z. We know what this solution is because this is just a Green's function. Green's function with the point source located at the origin. The solution is actually e to the ikr over 4 pi r. I'm going to switch over to this time convention now for physics and optics. Instead of for electrical engineer, okay? So I'm going to use this time convention, and let's see how we can solve this problem. And in the past, beta is equal to omega over c. Now it's k equals to omega over c in the optics convention, okay? So we are going to take a Fourier transform of v x, y, z and express it as a Fourier transform. And in order to express this as a 3D Fourier transform, we will have three-dimensional Fourier integral, dkx, dky, dkz. And then we're going to have the Fourier transform of this function, or this function, I will call it phi tilde in terms of the Fourier transform variables. And then write the transform integral. Let me write this as plus I k y y plus I k z z. Okay, can everybody see that this is just a simple rewriting of a Fourier integral? Can everybody see that? I'm just writing this, very good. And you can see that this is a 3D Fourier transform because I have this thing repeated 3 times. And then this thing also is repeated 3 times, okay? So very good. And now that you can see this, the question you might like to ask, when can I ever write something like this? When does a Fourier transform exist, like in 1D? Okay, if I have a function phi x, and then if I just want to write this as a Fourier transform e to the I kxx phi tilde kx. When can I do this? Does anybody know? You probably have studied this in some signal processing course and learned about this before. When can I do things like this? Well, the requirement is that phi of x has to be absolutely integrable. Okay, you can show this quite easily. The thing that you learn from signal processing or Fourier theorem is that if this thing is absolutely integrable, that is, if you take its absolute value and then integrate, and this is less than infinity, it implies that phi tilde kx exists. Okay, I'm not going to prove this, but it's something that you should keep in mind, keep at the back of your mind. Okay, and if you can do this, then you can replace this with the Fourier transform. This is also true in 3D. Okay. So now if you have this Fourier transform, then if you were to look at how Laplacian of phi, let me use a shorthand notation. This is just R. Okay. The Laplacian of phi would be just equal to 1 over 2 pi 3. And then I can take let me use a shorthand notation for this as well. I will call this decay bar. Decay bar means that it's dkx, dky, dkz. And then I take the Laplacian inside, okay? And I'm going to use a shorthand notation for this as k bar, okay? And then I have my Laplacian now operating on this. The only thing that depends on x, y, z is this exponential function, okay? And then I would have this been simplified to dk bar, phi tilde k bar, and then the Laplacian, because it's partial square, partial x squared plus partial square, partial y squared plus partial square, partial z squared will become minus kx squared, because when you differentiate partial x squared 2 times, it brings down a ikx 2 times, and then minus ky squared minus kz squared, e to the I. Let me use a shorthand notation for this. This will be e to the ik dot r. Is that okay? Can you see that I can write this in terms of this? Is this okay with everybody?
Yes.
Okay, good. So this is a shorthand notation. Okay, this is a shorthand notation. And I can write things more concisely and compactly using shorthand notation. Then what I have is that I can write the left-hand side of this equation. Okay, the left-hand side of this equation I can then write as, let me make this bigger so they can see better. Okay, the left-hand side of this equation is then, when you substitute in, I will have Laplacian square plus k square phi r is equal to 1 over 2 pi cube, a triple integral, okay, dk, and then I will have phi tilde k is kx, ky, kz, and then k squared minus kx squared plus ky squared plus kz squared. Sorry, it should be a minus. This should be a minus. E to the ik dot r. Can you see that this is equal to that? You can see from here, because the Laplacian itself is this, and if I were to add a k square, actually I use the notation k naught square. Let me keep it to be k naught square then. It refuses to write. K naught square. Okay. Then this is the left-hand side. The left-hand side now is expressible as a Fourier integral. Then what I need to do is also to express the right-hand side. Right-hand side is equal to delta x, delta y, delta z. And I can write the right-hand side as a Fourier integral as well. It's minus 1 over 2 pi cube. The Fourier transform of a delta function is a constant. So I can Fourier transform this, multiply by that, and multiply by that. I will have 3 constants of 1 multiplying together. And then the right-hand side will be just this. And then it's just 1. Okay, the Fourier transform is just 1. Essentially, this is just 1. Okay, so these two are supposed to be equal to each other. Okay, but these two integrals are supposed to be equal to each other for all x, all y, for all z. This is a math notation for all. Okay, this stands for all. So essentially for all r. The shorthand would be for all r. Okay. And let me see if we can move this away. Okay, so let me see if we can move further down or not. Okay, we can move it further down like this. So then when two Fourier integrals are equal to each other, we can say that the integrands are equal to each other if these integrals are equal to each other for all x, all y, and all z. Then you can say that the arguments, the arguments of the Fourier integrals are equal to each other. Okay, so if this is true, then we can say that v tilde kx or k, again, this one times k naught square minus kx square minus ky square minus kz square must be equal to -1. Okay, but this is not true if these two are not equal for all x, all y, all z. You can only equate the integrand when you can argue that these two integrals are equal to each other for all x, all y, and all z. This is very important. Okay, that is one very important mathematical step. Another mathematical step that we took is to have moved the Laplacian operator into the integrand. We have exchanged the order of differentiation and integration. That is, we plug this in here and then put the Laplacian inside. You can exchange the order of integration and differentiation only if you can show that the resultant integral converges. Okay, so this is only true. This being equal to that only if this resultant integral converges. Those are the mathematical fineries that we have to worry about, but let's not worry too much about that, and let's assume that this integral does exist. Okay, and this integral does exist, and if they exist and they converge, then these two must be equal to each other. Then I have an expression for my phi tilde now, the Fourier transform. Which is, if I write in a long form, which is kx, ky, kz, okay, it's equal to -1 over k0 square, kx square minus ky square minus kz square, okay? And then I can write my total field, the solution to this equation. In the beginning, I was setting myself out to look for the solution to this equation using a different technique. The solution I already know from the Green's function method to be this, okay? Now I have an alternative solution that this thing must be equal to, according to what I have now, 1/2 pi cube. I'm just plugging it back into this equation over here, okay? -1/2 pi cube, then integral, 3D integral, dk, which is using shorthand notation again. I put a minus sign outside, so it would be k0 square minus kx square minus ky square minus kz square. And then e to the ik dot r. Okay, so this is the shorthand representation for it. And this, if I write it down in full, is actually ikxx plus ikyy plus ikzz. Okay, so this is essentially a plane wave. So I have succeeded in deriving an expression that is kind of interesting. It says that this wave that I have derived before, given out here, okay, this wave that I have derived before, which is a spherical wave, can be written as an integral summation, a 3D integral summation of plane waves. This plane wave has the k vector, and kx, ky, kz, as I integrate, is going to vary over all possibilities. Okay, it can be written as an integral summation of plane waves propagating in all directions with different size of k vector. The k vectors can be of any length, because this can be going to infinity, this can be going from minus infinity to infinity, and this can also go from minus infinity to infinity. Okay, so this is only half the story, okay, because this integral is difficult to evaluate. It's 3-dimensional, and you have to integrate over many spectral components. Okay, so we want to try to elucidate more physics out of this integral. How do we elucidate the more physics? Then we have to do something called contour integration. And we have to simplify the thing by performing one of the integral first and say that this is actually e to the ikr. The left-hand side is e to the ikr over 4 pi r. Okay, the left-hand side should be equal to, we can write it in such a way that, let me see if we get things correct. Okay, it should be written as 1 over 2 pi cube. I can leave the dkx, dky integration outside first, and then I put the dkz integration in the innermost integration, okay? And I can write this as kz squared minus k naught squared, okay, minus kx squared minus ky squared. I'm just reversing this row. I'm just reversing that so that kz becomes the leftmost thing, and I'm going to take this minus sign away, okay, and say that it's just a plus sign over there. And then I will have this. Let me just write one of the integrals here, okay. The other two integral, the two exponents, let me put them outside. Okay, let me put them outside, e to the I kxx plus I kyy. And then I will have only one that is in the innermost. Okay. So let me see if I can integrate this in closed form. Okay, let me see if I can integrate this in closed form. And it turns out that you can integrate it in closed form if you know how to do contour integration and using Cauchy integration principle. Okay, so how do we do that? Well, if you have some knowledge in this, then it'll be very simple. And if you do not have knowledge in this, it's within your reach as to how you should do this. This integral is an integral, a Fourier integral in the complex kz plane. Okay, this is complex kz. Okay. Okay, this is real kz. This is imaginary kz. I'm just writing out this integral in the complex kz plane, and it would be an integral something like this. Okay. I'm integrating on the real axis. And this is what I do as I integrate from minus infinity to plus infinity. Okay, can you see that? Okay, I'm going to minus infinity to plus infinity. And they are poles in the integrand. The poles are given by when kz equals to that. So when kz, the way I have written down the denominator, I can see that if kz equals to k0 squared minus kx squared minus ky squared, okay? If kz equals to this value, then the denominator would go to 0, and this would be a pole. And you can see that there is a pole, there should be a pole here. Okay, that pole location is given by square root of k0 square minus kx square minus ky squared. And then there is another pole that is diametrically opposite to this. So if you take the minus sign, you'll be given by this. Okay, and then you can use Cauchy integration technique that says that the integration along the horizontal axis, the real axis, will be the same as integration along the horizontal axis plus this integration. Okay, and this additional integration that I have added contributes to 0. Okay, you can show that that contribution is 0 by Jordan's lemma. Okay, invoke Jordan's lemma. And if you go through some detailed arguments, you can show that this integration is in fact very, very small, because the integrand, if you look at it, the integrand with kz going to infinity, here is the value where kz becomes very, very large. And you're going to take this contour to infinity, and kz will become very large, and this will be 1 over kz squared. Okay, this will be over 1 over kz squared. But this thing will only grow as kz. Okay, and you can show that because of that, the integrand actually contributes to 0. I will not go through this, but it's shown in very many complex variable textbooks. Okay, by Jordan's lemma, this goes to 0. So by the argument then, this contour integral along the ray axis is the same as the contour integral along the ray axis plus this integration. Okay, but this integration contributes to nothing, so I have not changed the integration value at all. But then you know that if you have a contour, integration of a contour around a circle, and if there's a pole in this contour, do you know how to do the integral? Okay, how many of you have not had a course in complex variables? I suppose all of you have had a course in complex variables. Am I right?
Yes, I have one.
Okay, good. So if you were to integrate this around a circle, you can show that if something is analytic, if you integrate around a circle, that contour integration to be 0. But this thing is not analytic, it has a pole. So it doesn't integrate to 0, but you can make it go to 0 in the sense that the integration along this contour is the same as the integration along this contour. You can always add something like this to the contour and argue that these two cancel each other. And then the only thing left you have is this Cauchy integration around the pole. Okay. Finally, you're left with the fact that integration around big contour around a small circle. Okay, any questions so far? So I can use Cauchy's integration theorem to say that integration around the big contour is the same as integration around the small circle around the pole. And that is called taking the residual of the pole. Then you can approximate that integration around the pole quite easily. Okay, you can approximate the integration around the pole quite easily and obtain the closed form. Okay, you can obtain a closed form, and that closed form is obtainable by doing a residual calculation. And I will not go into the detail, but you can read up about it in the lecture note. And finally, you have that the integral, what you have left is that of the 3 integrals that I have had before, one of them can be performed in closed form using Cauchy integration technique, and I'm only left with a 2-dimensional integral. okay? X, sorry, this should be KXX plus KYY. And then if you do the Cauchy integration technique, then it will pick up the value at the pole location like this, okay? And then the residue of the pole give you something like KZ prime. And then there were some factors like 2 pi I or something like that somewhere, okay? Because you have to pick up the residue of the pole. Okay, and this is usually documented in most complex variables textbooks. Okay, so is this okay if I don't go to the detail that if you were to perform the Cauchy integration of this pole, you get this value over here. The residue is given by this. Okay, and this is for z larger than 0. You can show that the contribution to the contour here is 0 only if z is positive, because over here, kz is very large in its positive imaginary value. So if z is positive, then this thing becomes exponentially small. So you can only detour upward only when z is larger than 0. Okay, and if you were to repeat this exercise for negative z, because the value of z can be both positive and negative in this integration. Okay, z can be positive and negative. And if z is negative, then you actually have to detour the contour downward. Okay, this is for z positive. And if z is negative, you have to detour the contour downward. Okay, and if you do this exercise again, you will pick a residual, you'll pick up a residual of that pole down there in the lower half plane. And finally, the thing you get is that you will get a different sign for the residue, and you will get e to the minus I kz prime z because of the negative sign there. And then you will have a kz prime that's negative, but because you're going in the other direction when you pick up the residue, the residue is now being picked up in this direction, so that minus sign cancels. And what you have is that finally you have something like I over 2 pi square, a double integral dkx dky e to the I kxx plus I kyy e to the I kz prime z because of the change of the sign over kz prime. Okay, so that triple integral becomes a double integral, where kz prime is the value of kz at the pole location. Okay, because you have to perform this residue, and the value of kz has to be the value of the pole location, which is this value over here. So kz prime now is equal to k0 squared minus kx squared minus ky squared. Okay. So is this clear? Are there any questions so far? Well, actually, I have this nice picture that I have for my textbook. Okay, so this is how the residual calculus goes. You have two poles, one here, one there. You pick up the residual contribution. But now you have a rather beautiful expression. It says that the solution can be expressed in terms of a double integral. The left-hand side is essentially a spherical wave. Okay, and then it says that I can write a spherical wave which is, let me change my pen. This pen seems to be giving some problems. Okay, the spherical wave now is I over 2 pi square over dkx, dky, e to the I kx plus I kyy plus I kzz. I'm not going to write kz prime now. I'm just assuming that kz is kz prime. Okay, kz is just kz prime. I'm not going to write it as kz prime. It's just kx squared minus ky squared. Kz squared minus ky squared. So kz is the value of the kz value at the pole location, which is given to be this. Okay, so this is a beautiful expression because right now we have a plane wave on the right hand side, but this is a true plane wave in the sense that kx squared plus ky squared plus kz squared is k naught squared. Because the way kz is now, okay, kx squared plus ky squared plus kz squared must be k naught squared. Previously, we don't have this nice property in the sense that when we had the Fourier integral, when we first derived this expression over here, okay, kx squared plus ky squared plus kz squared can be any value, and it's a 3D Fourier integral. But now we have reduced it to a 2D Fourier integral with the requirement that kx squared plus ky squared plus kz squared must be equal to k naught squared. Okay, so it satisfies the dispersion relations of free space, of plane wave in free space. Okay, so this is now a physical plane wave instead of a mathematical plane wave. Okay, so I'm not going to show you the detail, but this is wonderful in the sense that we have a spherical wave, and then it actually looks something like this if I were to sketch it out. Okay, but on the right hand side is just a linear superposition of plane waves propagating in all directions. You can think of it as plane wave propagating in all directions. Okay, and this is z, and this is x and y, and so on. And it also includes evanescent wave because there will be values of the kx and the ky, or values of kx and ky that is larger. Okay, when kx squared plus ky squared is larger than k naught squared, because you're integrating over all possible kx and ky value, and then if that happens, you actually have evanescent waves, because when that happens, kz becomes pure imaginary. Kz is pure imaginary. So this integration summation is over all propagating plane waves as well as evanescent waves. Okay, and there's another beautiful thing that you can do, which is to rewrite this integration in cylindrical coordinates. You can use a cylindrical coordinate transformation. Instead of integrating this in Cartesian coordinates, you can integrate this in cylindrical coordinates. I will not go through the detail, but it's written up in the textbook or in the lecture notes. And then you can write this as a integration summation. Okay, in cylindrical coordinate now, k rho is the variable in the rho direction, and then you have a Bessel function, and then you will have e to the I k z z. Okay, you will have this thing. Let me draw a line here to think. The good thing about this is that this is a double integral. This is a single integral. And it's a lot better for numerical integration because it saves computer time. Instead of integrating from minus infinity to infinity, you only need to integrate from 0 to infinity. And k rho is the k vector, like if you have kx, ky, okay, if you have a Cartesian coordinate system, if you have a k vector, okay, this k row would have xkx plus yky. And if you were to go to a cylindrical coordinate system, okay, then the kx, the ky will become a 2 pi k rho d k rho, okay, because of the cylindrical symmetry, you can show that this to be true, and then you can convert this integration into just a decay row integration. You can do a change of variable as well, because kx squared plus ky squared should be equal to k rho squared, which means that if you were to do change of variables, you will have something like this, k rho, and then you can do change of variable to dkx, dky, where this change of variable. So it's pretty elementary kind of algebra, but after you've gone through the work, you have this beautiful integral. This integral is called the Summerfield integral. He derived this in 1909, okay? And this usually is called the well integral. Well integral, or the well identity. And according to the literature, it was derived in 1919. Okay, I believe that Summerfield must have derived it before well, but everybody called this the well integral and well identity. And Summerfield just published this work in 1909. Okay, any questions so far?
Does the Summerfield integral always converge?
Yeah, it converges if you pick the integration path correctly. Okay, and it converges if you assume a little bit of loss. There's some fineries that I didn't go through, which is that when you perform this integral over here, yeah, that's a very good question. This integral does not exist if this pole is right on the ray axis. Okay, if this pole is right on the ray axis, when I perform this inversion contour, for instance, it does not exist. So in order for this integral to exist, you have to introduce infinitesimal loss. If you make k0 squared to be slightly lossy, then this pole will be moved off the ray axis and will look something like this. Okay, move off the ray axis. And then this Fourier inversion contour or Fourier inversion transform would exist because it collides with no poles. And this integral is well defined. And once you can show that this exists and it can be performed in closed form, this identity exists if you have a little bit of loss in the medium. If there's no loss, then you're in trouble, okay? And hence you can show that the Summerfield integral or Summerfield identity also exists if there is an infinitesimal loss, okay? So we have to introduce infinitesimal loss, and you have to kind of introduce them so that the integration path can be below this singularity and above this singularity when you're working with this Summerfield integral. Okay, that's a good question, and I will not belabor this point because more interesting thing is to solve the radial problem. The radial problem is to put a source on top of a layered medium. In that case, and during Summerfield's time, he was just putting it in top of a half space. Okay, but what we have derived so far actually allows us to put this point source on top of any layered medium because we have enough knowledge at this point. And the physics is quite clear. The physics is that we expand the spherical wave in terms of summations of plane wave. And in order to expedite computation time, we expand this plane wave in terms of cylindrical waves. Okay, but in the z direction is still a plane wave. And we know that if this source is now radiating plane wave in the z direction, but cylindrical wave in the rho direction, we would know how to bounce this wave off a layered medium. Okay, it can be make homomorphic to a transmission line problem. Okay, so the idea then is that if I have a point source, it produces spherical wave, but lo and behold, I can change that spherical wave into summations of plane wave using Summerfield identity or real identity. Okay, so the next thing I have to do then is to actually figure out how to put this problem so that I know how to solve it when a point source on top of a layered medium. So I would know that I first expand the wave into plane waves, and there are two kinds of waves in a layered medium. What are the two kinds of plane waves that can propagate in a layered medium? Do you remember? When you solve the layered medium problem, we cannot just propagate any plane waves, but the plane waves are decomposed into two kinds. Maybe I make the problem simpler. For the single interface problem, if we have an electromagnetic wave incident on a single interface problem, how must we decompose this plane wave into what kind of two plane waves in order to solve this reflection problem? Do you remember what we had to do?
TM mode components.
Very good. Yeah, very good. Excellent. We have to break this into TE and TM polarization. Okay. Similarly, when we put a point source on top of a layered medium, the point source is going to generate spherical waves. But we know how to expand these spherical waves into summations of plane waves now. And after we have expanded those into summations of plane wave, we have to break that plane waves into TE and TM types. So we might as well do it early, okay? Since we have this hindsight that this what we need to do. So we will look at a electric field from a Hertzian dipole. The electric field from a Hertzian dipole is given by this expression. I think you have seen that before, okay? You have seen that before, but it's given by this expression. If you were to use the dialectic Green's function, you can derive this using the vector potential approach as well. So if you have a Hertzian dipole, then the field produced by a Hertzian dipole is given by this expression. You can use that directly from the dialectic Green's function, and if you don't like the dialectic Green's function, you say that this is just I omega A mu A. Okay. No, I omega A, sorry. I omega A minus grad phi. Okay, you go to the scalar potential approach and the vector potential approach. You find those when you have a point source, you plug that back in. You find that after you plug that back in, you get an expression something like this. Okay, or you can directly go to the dialectic Green's function method where you have done a little bit of that in your take-home exam. If you are not comfortable with that, you can go back to your fundamentals, work with the vector and scalar potential approach and apply Lorentz gauge. Okay, so E is given by that, where the current in this problem is just an arbitrarily polarized Hertzian dipole located at the origin. Okay, and I think we can derive the above quite easily using this expression if you still don't feel comfortable about it. But I can use the dialectic Green's function approach. Okay. And you have seen some of this in your exam, your homework, in the take-home exam, where this dialectic Green's function G you have shown in your homework by back substitution that it looks something like this. Okay. Okay. So E is given by that, and you can easily also obtain the magnetic field due to a Hertzian dipole by invoking Ampere's law, no, sorry, Faraday's law. Okay, and then you can find that this will give you something. The curl of a gradient is always equal to 0, so this thing drops out, this term drops out, and you're left with only the first term if you take the curl of E, and then you will have this e to the I k r over r. Okay, 4 pi r, sorry. Okay, so you can easily write down the electromagnetic field due to a Hertzian dipole pointing in arbitrary direction using very compact notations here. Okay, but we have the hindsight that we must break this field into TE and TM type. We might as well break them before we break them into summations of plane waves. So if it's TE to Z, then the field must be of the kind of HZ is not equal to 0, EZ equal to 0. If it's TM to Z, okay, then it will be of the kind where EZ is not equal to 0, HZ must be 0. Okay, with this hindsight, so we may as well pick up the TM component, for instance. If you want the TM component from this, we find EZ. Okay, EZ not equal to 0. Okay, we want TM. We look for EZ not equal to 0. And then you look for terms that give you EZ not being equal to 0. It's quite easy to do. You can assume that, let me see, in this particular case, I'm doing the case where Z, okay, I'm doing the case where Z, where alpha is equal to Z hat. Okay, I'm doing the particular case, you can plug it in and also make alpha Z hat the expression that you finally get after plugging in the Summerfield identity for the spherical wave that, oh, sorry, this is not, it goes from 0 to infinity, the k rho cube over kz. Okay, I'm using Summerfield identity into this spherical wave expansion here. And then okay, it's a kind of a plug and chuck thing that you expand this using Summerfield identity. You make alpha points in the z direction, and then you go through the algebra here, which is second derivatives and so on. It turns out that finally you will obtain a k rho cube up here. But the important thing is that this EZ now is expanded in terms of plane wave expansion. Maybe not apparent to you, but this is actually plane wave expansion in disguise, because you can actually rearrange this integration in cylindrical coordinate. It becomes summations of Bessel waves plus plane wave in the z direction. Okay, and if we know how to propagate plane wave in the z direction on top of a layered medium through a layered medium, then we know how to solve this problem when we put this point source on top of a layered medium now. Okay, let's do that. But before I do that, let me ask if there's any question so far. Any question on the derivation? Okay, so if there's no question, then we are ready to go. We know how to expand the point source field in terms of plane waves, summations of plane waves. Then if we were to now put it on top of a layered medium now, we are very good at layered medium because we have used transmission line theory to solve this many times over. And let's assume that this particular electric dipole is pointing like this, okay? And it's at the height d1 above the interface. And let's assume that we have mu1, epsilon1 in that medium over there, okay? So this was expanded in terms of spherical wave, which in turn can be expanded in terms of plane wave. And I just have to figure out how to find the reflection of this plane wave as it bounces off this medium. So I can write down the solution in region 1 without the reflection. It would be something like this. Okay, the k row. Let me write this k row properly. The k row cube over k1z. I have to be mindful that it has to be k1z and not kz alone because I'm in region 1. Okay, in region 1. In region 1, the dispersion relationship is that k1z plus kx squared plus ky squared, which is the same as k1 squared plus k rho squared. This is just k rho squared, must be equal to k1 squared. Okay, this is my dispersion relationship. So my k1z assumes a different value. Okay, and then if I don't have a layered medium below me, I just have this as my solution. Okay, but if I have a layered medium below me, below this dipole location, let me put it properly, I would just have to add in a reflected wave term. If it is just one interface, I will have just added a simple reflection coefficient for a TM wave because E1Z not being 0 is a component of a TM plane wave. And then I just have to keep track of the phase to make sure that the phase that I add actually correctly defines this reflection coefficient. The wave that I add has to propagate upward. If this is my Z direction, okay, it has to propagate upward. And then it has to be such that I have to add the correct phase. This should be K1Z, sorry, A, K1Z, A1Z, D1. Okay, this is the correct phase I have to add to this wave because when Z equals to minus D1, this is Z equal to 0. Okay, this point here, Z equal to 0. So when Z equals minus D1, the ratio of these two waves is just R1 to Tm. Okay, you can set Z to minus D1. Okay, you'll find that this wave will have the phase of e to the ik1z d1, and then this phase will be ik1z d1. Okay, so they have the same phase now. If I set Z equals to d1, I put in this phase judiciously so that when it's set Z equal to minus d1, they have the same phase, and the ratio between them must be the reflection coefficient. Okay, so that's how I pick the phase judiciously. And lo and behold, now I have a spectral expansion of the field in terms of plane waves. And I have been even able to find a reflected wave. And you can use the same thinking that if I were to follow the transmission line theory, I can figure out all the fields in each of the respective regions. Okay, and those will be some details that you have to learn in your I guess by studying the lecture notes. Any questions so far? Any questions? So no question, then I'd like to move on to a different topic, which is the way to approximate these integrals in a very clever fashion. And these integrals are very complicated, and they don't offer you much physical insight other than the fact that they're plane waves bouncing around like in transmission lines. But I'm going to say pick a complicated expression and just pick the reflected wave term, for instance. It's going to look something like this. Let me put everything that's complicated. And then I'm going to put everything that is complicated and call it f of k rho. Okay, I'm going to put this factor, everything in there. And then what I have left is just e to the I1kz plus 2I1kz d1. Okay, so this thing is very, very complicated. What can I do to expedite is the integration. Well, I can use what is called the method of stationary phase. Okay. What this method does is that it is better to use the Weyl identity, reverse this integral summation, and write this as a Weyl identity kind of thing. Then I will have a double integral again. Okay, e to the I k x x plus I k y y plus I k z z plus 2d1. And then I will have a k1 z here, and then this very complicated function, kx, ky. This is a very complicated function of kx and ky, okay? And then the stationary phase method will say that if this thing is integrating, or if I want to integrate this function over all kx and ky, I'm going to see that the integrand is going to be rapidly oscillating if xy go to infinity and z plus 2d1 go to infinity. You can see that when this is large, a little bit of change you make to kx, a little bit of change you make to ky, the integrand is going to change rapidly. Also, if z plus 2d1 is going to be very large, a little bit of change you make to kz, the integrand is going to oscillate wildly. So you use these concepts thinking that, well, if I were to say, think of this as a one-dimensional integral, the integrand is going to be rapidly varying like this. Okay, I'm just illustrating this with the kx integration. That when x and y is very large, say when x is very large, the integrand is going to oscillate like that. And there will be some points, okay, because kx is also buried in here. Kz, remember, is k1 squared minus kx squared minus ky squared. Okay, so there will be some value of kx where the phase is stationary. This point is stationary phase point. You can see from this picture that most of the contributions to the integration will come from around the stationary phase point. Okay, so what you can do is that if this is rapidly varying, okay, this is not rapidly varying, I can actually approximate this function around the stationary phase point and say that now I can find out the value of where the function is stationary phase. Where the stationary phase points are, take this function, approximate around that stationary phase point, and then just integrate this. And this is a lot simpler now. Z plus 2d1, okay, over k1z. This one you can integrate in closed form because this is just the Weyl's identity. So you can integrate in closed form. It will be something like ak1r over ri. Okay, you will go and look in the detail in the lecture note. And this is one way you can approximate this very, very complicated integrals. You use the stationary phase method. And essentially, what it says is that if you're far enough away from this interface, or if you go far away, everything looks like a spherical wave again, okay? So everything can be approximated as a spherical wave. That is, if you look at the reflected wave, if a source here, if you just look at the reflected wave, even though it looks very complicated, it actually looks like a spherical wave bouncing off an interface like that. Okay, I will write up this in greater detail in the lecture notes. Okay, any questions so far?
I have a question on this function f of kx, ky.
Right.
How do do you actually pick up it? I mean, where I can see this kind of function shaped in such a way?
Fkx and Fky is a function I conveniently define to put all the complicated terms like R12 inside it and put this constant inside it. Okay, and all the salient feature of the face I kept outside. So you can think of F as being, if you think of it as a Fresnel reflection coefficient, you will have quite a bit of complicated expressions in there if you remember how the Fresnel reflection coefficient looked like. Depends on K1Z and K2Z and so on. But those are too complicated to write explicitly. I just lump them inside. But those are not going to be rapidly varying functions of Kx and Ky. So when x and y tends to infinity, the stationary phase point is a point that will contribute to the integral. And I just have to integrate around that stationary phase point, take this thing, approximate around the stationary phase point, take it outside, and then just integrate this in closed form. Okay, so you will see more of this in your homework. I will give a homework where you have to find the stationary phase point. Okay.
Yeah,
okay.
that I wanted to ask the next question, that how to find the stationary point, but okay, I'll figure it out.
Yeah, this is described in detail in the lecture notes. Okay, you take the derivative of this function with respect to Kx and Ky and set it to 0. And it's an algebraic problem, and then that will allow you to find the stationary phase point. Okay, I'd like to move on to the next lecture, lecture 36, which is on computational electromagnetics. Okay, and talk about some of the concepts that we have there. Okay, and computational electromagnetics is very, very important because of the advent of computers. Computers are so fast now, they can compute at blinding speed. Okay, they have things that goes as teraflops and even more. Okay, so when I look at how fast computers have progressed, I always have this memory of a quote by Dyson, John Dyson. Technology is a gift of God. Okay. Because we have so many technologies around ourselves, and they actually do wonderful things for us. Computers being one of them, plus many, many other things. Okay. So let me describe how we can use technology to help us solve complicated problems. We have been trying to solve complicated problems using analytic method, and you know that takes a lot of brain. Okay, but we can also use computers to help us solve very, very complicated problems. Let's just think of a problem that is not solvable ordinarily. That is, if you have a wave equation where we have a source, okay, when this is inhomogeneous. If this is a constant, of course, we know how to use the Green's function technique to solve this problem. But if this is inhomogeneous, then we don't really know how to do this using any closed form or Green's function technique. Or we have a vector wave equation that we need to solve. Okay, this equation might look something like this. Or it might be in homogeneous media. Okay, and then the right-hand side is a source term. Okay, it's a source term, and we don't know how to solve these problems using closed form or analytic solution or Green's function technique. Okay, so let's think of this as linear operator equation. You can think of these equations have been solvable if you define them in terms of linear operator, where the linear operator L can mean this operator in the scalar wave equation, or it can mean this operator, the differential operator minus omega squared mu epsilon in the vector wave equation. And this is a scalar wave equation. Okay. And then G can be the term, the driving terms on the right-hand side. G can be the source term for scalar wave equation, or in the vector wave equation is just this term. So, but what is important is that this is a linear operator. Okay, this is linear. And you need boundary conditions. Okay, boundary conditions for uniqueness. Okay, you need to stipulate what the boundary condition should be when you solve this differential equation. Okay, so you can also have integral equations using Green's function techniques, where you would say that, well, I have I have, say, in 1D would be something like this, that you can think of a Green's function operating on 1D, and then it will be something like this. Okay, this is an integral equation. Okay, so this is usually called the kernel in integral equation, kernel. This is unknown. This is known, the driving source. Okay, so again, it is of the form of LF equal to G. So when you have an integral equation, everything can be written in this very nice form. Then the question is, how do we solve this linear operator equation? How do we solve this linear operator equation? Well, the way to solve this linear operator equation is actually to find a way to convert them to a matrix equation. We would like to find a way to convert this linear operator equation into a matrix equation such as this one. And this can be done by what is called the subspace projection method. Okay, subspace projection method. And how do we do that? Well, you imagine that you have this function f. Like if f is in 1D, okay, you can expand it in terms of sets of basis functions. You can approximate your 1D function or some function in this manner. For instance, in 1D, you have this f of x. And f of x might look something like this. And if you approximate this in a piecewise linear fashion, you can think of them as summations of triangular functions. Okay, sum of triangular functions. And you can think of this f sub m being triangular functions and sometimes called the chapeau functions. And this is called the basis function. Okay, so if you do that, then if a function can be approximated by sums of basis functions, then you can plug that into your linear operator equation. Then if you exchange the order of summations and operation, the operation can be integral or can be a differential. Then you have this equation that looks something like this. Okay. Okay, so this equation will become something like this. It's not the matrix equation yet, but you can choose to multiply this equation by W sub m. and integrate. And let me call this the inner product. Okay, so when I have like in 1D Wm of x, g of x, I'm going to integrate it. I might integrate it from minus infinity to infinity, but this is subdomain, so it doesn't matter. Okay, if the W sub m is also a Chapeau function or triangle function, I can pick my range of integration to be infinite, but it will only pick up the integration over places where W sub m is non-zero. And usually this can be written as a shorthand notation as an inner product between W and G. Okay, so I multiply this equation that I have from there, and then finally I will have AN WM L Fn is equal to Wm G. Okay, I have this thing, and this goes from n is equal to 1 to n. Okay, so if you look at this equation now, I started with a linear operator equation. I make a basis functions approximation and multiply it by a weighting function. This is called a weighting function or testing function, is weight or testing function. Okay, it's called weighting function or testing function. And then let me use a new slide. Okay, and then you essentially have something that looks like a matrix equation. Now, if you look at this equation in proper, it essentially is Lmn an n is equal to 1 to n is equal to like Gm. Okay, where I define my Lmn to be equal to Wm L G Fn. Okay, and then my Gm to be equal to Wm G. So this is a matrix equation now, and I can choose my weighting function or testing function so that it goes from 1 to n. And then I have enough equations to convert this into a matrix equation. If that happens, then I will have this being writable as G, where this is now n by n matrix system. This is n by 1 vector because an goes from 1 to n. And then this one is n by 1 vector. And then I just need to solve this equation. And nowadays, we have digital computers that can use to solve these equations with a blinding speed. Okay, with a blinding speed. And even though it may look a little bit naive and kind of silly to do things like that, but it allows you to solve problems that is not solvable in closed form. A lot of the things you learn in this course have closed forms, but most of the problems that we have in the real world do not have closed form solutions. And you have to resort to converting those equations into a matrix equations and solve them, okay? And this is the gist of it. Any questions so far before I let you go? Any questions?
What is the physical meaning of those testing functions, Wm?
Or Wm essentially it's more mathematics and physical meaning, that you try to equate two equations to be equal to each other. I have an equation when I plug this in before testing, I have an equation that looks more like, let me write it down here. Before testing, I have an equation that looks like L, okay, an Fn, n is equal to 1 to n, equal to G, okay? I want these two equations to be equal to each other. And I know that they are like functions in infinite dimensional space. I want to force them to be equal to each other over the domain or the domain of the testing function. So I'm going to, I can actually say that, well, I can put in x here. I want to multiply them by x and then integrate. Integrate, okay? I'm actually forcing these equations to be equal to each other over the domain of the weighting function. The places where the weighting functions are not zero. And I have to keep repeating this. I have to keep repeating this until I have tested this equation enough. Okay, so that when I do this, then I have to pick my m to be over many possible values so that the equations are well tested. It's called well tested. That means that you have forced these equations to be equal to each other numerically over a large number of functions. And if you force two functions to be equal to each other over enough vectors, okay, then you can actually find them quite easily. And if I want to give you, if I want to give a geometrical interpretation, maybe I can use a 3D space. Okay, so if I have a vector v that I don't know which direction it is pointing, okay, I can find the component of this vector v in the x direction and the y direction and the z direction by testing. So these are called inner products. These are called inner products. So I can also write these three equations that I need by finding the inner product of this with that, and that would actually be very simple because it would be just x dot v. Okay, I can find the inner product of this v with y hat. Okay, that would be just y hat v. Okay, and then this would be just z hat v, which is just z hat v. So you can think of it as taking components of this abstract vector in a Hilbert space and force them to be equal to each other in certain component-wise directions. You can think of them, they don't have physical meanings, but they have mathematical meanings. You're taking a component of that vector in an infinite dimensional Hilbert space, or abstract vector space, and force them to be equal to each other. Okay, does that answer your question?
Yeah, because I was looking on this, it's kind of projection. We take projection, meaning that WM is kind of basis in Hilbert space.
Right, right. You are projecting onto those vectors and force them to be equal to each other. And those vectors that you project to better be independent of each other. If you project them to be on top of vectors that are dependent on each other, you're not finding new information about this equation. Okay, your WMs better be independent of each other. Okay. Okay.
Yes, this makes sense. Thank you.
Okay. If you read the lecture notes and if you have questions, let me know. I'm polishing the lecture notes, and as soon as I have polished them, I'll send them to you. Okay, I'll let you go. And tonight's office hours will be conducted by Dr. Dong-Yup Na. He will give it at 8 p.m. tonight. Okay? And you can ask him questions too if you have any questions on this lecture.
Thank you. Bye, Professor Chu.
Yeah, I'll let you go. Let me see. How do I stop this? I stop share. And then I end meeting for all.